Okay, this is Mr. Hammond, and this practice problem is going to be an advanced pulley problem. You can see our setup here. This is really a very popular physics um, practice problem because it does a great job of combining a lot of things that you may have learned already about Newton's second law, about the acceleration due to gravity, and about the force due to friction. So we're going to start going through this as we've done with videos in the past. If you already know what you're doing with a problem like this, it might be in your best interest to pause it and work the problem out on your own and then check your answer as you go. Or if you're just learning for the first time about this problem where you really need a lot of review, we're going to go through it step by step. So here's the problem. It says there's a 0.25 coefficient of friction between the 5 kilogram block and the ramp. That's the yellow block. What is the acceleration of the system? So we have the yellow block being pulled up the ramp, and the force that's being applied to the yellow block is being provided by the 12 kilogram orange block being accelerated due to gravity. And you can see that the incline of the ramp is 20 degrees. So we're looking for the acceleration, and so here's our setup again, and a variation of Newton's second law is that the acceleration is equal to the net force divided by the mass. So that's what we're going to go for here. So we have a lot of steps to take care of to get back to A equals Fn over m, but we're going to start piecing it together and using this information that we get to ultimately get the acceleration of the system. So we don't have Fn yet, but we do have the mass of the system. The mass of the system, this is important in this type of problem. When we're using the mass of the system, or we're using Fn over m, the mass is the combination of both blocks. It's 5 kilograms plus 12 kilograms because they're working together, they're being accelerated together, and so their mass needs to be combined. So that just leaves us with a Fn over 17 kilograms. Now we don't know what the Fn is yet, so we're going to have to do some work for that, but we can at least get that far as our Fn over m. All right, well, let's look at the net force. We know that the net force is equal to the applied forces minus the opposing forces on that 5 kilogram block. Now, we know the applied force is going to be provided by the acceleration due to gravity on the 12 kilogram block because it's attached with that red rope there. The opposing forces, we're going to have to do some work to get the opposing forces, but let's talk about the applied forces then. Remember, the goal is to get Fn. We need Fa and we need Fo. To get Fa, we're just really looking at the acceleration due to gravity, the force due to gravity on that 12 kilogram block. So if we have a 12 kilogram block and it's being accelerated at 9.8 meters per second squared, then we know that the force applied is 117.6 newtons. That's just taking the orange block. Now, again, we have two blocks in this system. When we found the mass, we had to combine the two blocks when we were looking for the acceleration, as we did at the top there. When we're talking about the force, the 5 kilogram block is not involved in the applied force. Only the 12 kilogram block is being applied with the applied force. And so in order to get the force applied, we only use the 12 kilogram block. I hope that makes sense. So it's 12 times 9.8 to get 117.6. All right, well, we're getting closer to finding our net force, but we still have some work to do. So we have the applied force. That's the only force being applied to the 5 kilogram block. Now, there are some other forces on it. There are going to be opposing forces. Let's start taking the steps to find the opposing forces. There are really two opposing forces on the 5 kilogram block. We have Ff, which is the force of friction. That's going to be resisting the motion as the block is being pulled up the incline. And we have the parallel force. The parallel force is the percentage of the block's force due to gravity that is acting parallel to the surface of the incline that's trying to pull it down the incline. If there was no string attached to that 5 kilogram block, it would naturally slide or want to slide down the block because of gravity, and that's because of the parallel force. We're going to do some work to find the force of friction and the force parallel so that we can find the opposing force and ultimately the net force. Alright, so a lot of steps here. Like I said, this is a great problem because it really summarizes almost everything we've learned so far up to this point. Alright, so let's look at that 5 kilogram block. If we were going to draw a force diagram on this 5 kilogram block, this is how we would start. The weight of the block goes directly towards the center of the earth, goes straight down. The normal force, alright, the normal force, which is the force perpendicular to the surface between the block and the incline, is going to go along that blue arrow. Now that 20 degrees is important. We're not going to take the time to show you this, but that angle of 20 degrees of the incline is also the angle between the object's weight and the normal force. Those two triangles are going to be similar to each other. So we're breaking the weight into its components. The weight, due to gravity, is going to be divided between the normal force, which is that blue line, and the parallel force, which is my green line, my green arrow. Depending upon the angle, that's how the weight is going to be balanced between the normal force and the parallel force. If there was zero angle, then all of the weight would be the normal force and there wouldn't be a parallel force. But in this case, there's a 20-degree angle. So part of the weight is the normal force, the blue arrow, and part of the weight is the parallel force, the green arrow. Well, we know what the weight is. The weight is m times g. Using SOHCAHTOA, we know that the green arrow would be the weight times the sine of 20 degrees. We know that the blue arrow would be the weight times the cosine of 20 degrees. If you look at that, the weight, that red arrow, it looks a little bit sideways, but that red arrow is actually the hypotenuse of a right triangle. So the weight, being the hypotenuse, can be used with that 20-degree angle to find what we need. Alright, so let's do the weight first. The weight is mass times gravity. The mass is 5 kilograms. The gravity is 9.8 meters per second squared, and weight equals 49 newtons. So the weight, that red arrow, is 49 newtons. Now again, how that's distributed between normal force and parallel force is important, so let's figure it out. Let's do the parallel force. The parallel force is going to be the weight times the sine of 20 degrees. Therefore, the parallel force is 49 sine 20, which is 16.8 newtons. So because of the weight of this 5 kilogram block, there's a force of 16.8 newtons down the incline of the ramp. It's trying to pull it down. That's just the force due to gravity on that yellow block. Alright, well, what's the normal force? The normal force is going to be important for us to calculate the friction. So the normal force is going to be the weight times cosine of 20. 49 cosine 20 is 46 newtons. So the normal force is 46 newtons. So now we have our weight, we have our normal force, and we have our parallel force. So going back to our original diagram, we now know that the opposing force, which is made up of two forces, there's two opposing forces on my yellow block, the force due to friction and the parallel force. The opposing force is part of it is the parallel force, which we just calculated at 16.8 newtons. So one of the two opposing forces we have done, it's the parallel force, and it's 16.8 newtons. We have one more opposing force to go. That's the force due to friction. Well, we know that the force due to friction is mu times the normal force. The force due to friction is mu, which is the coefficient of friction, times the amount of the weight that's perpendicular to the surface of the incline. So we were given mu, which is 0.25, and we already calculated the normal force, which is 46 newtons. So if you multiply those two together, the coefficient of friction times the normal force, you have a force of friction of 11.5 newtons. So finally, we have our two opposing forces, 11.5 newtons from friction, 16.8 newtons from the parallel force. Our total opposing force is 28.3 newtons. That can be put into our net force equation on the left side of the screen here. So we can calculate our net force. Net force is 117.6 newtons minus 28.3 newtons. We finally have a net force that is acting on the yellow block, 89.3 newtons. Okay, one last step. We know, going way back to the beginning here, that acceleration was net force divided by mass. The mass of the system is the combination of the yellow and the orange blocks, 5 plus 12, which is 17 kilograms. The net force is the combination of the applied and the opposing forces. The applied force was 117.6 newtons. The opposing forces, friction and parallel, combined was 28.3 newtons. So the net force was 89.3. We put that into our original equation. We have 89.3 newtons for our net force, 17 kilograms for our mass. Acceleration is net force divided by mass, 5.3 meters per second squared. So there's a lot of work there, there's a lot of steps, but it really reviews all of the important topics we've dealt with so far. And again, that's why this problem is so common. That's why this is practiced in almost every physics class that deals with these topics, because it is a great summary of what it is that we've learned and that you've learned so far.